This is the light matter section of 2012. So we're starting off with photoelectric effect. So here's a person VCE, uses two metal plates in the photoelectric cell, one zinc and one's aluminium. So they're different plates, they'll have different work functions. Uses light of a particular frequency to illuminate the zinc plate and the aluminium plate, but finds that the photoelectrons are only emitted by the zinc plate. The threshold frequency for zinc is this, and aluminium is this. Calculate the maximum wavelength of light required to emit electrons from the zinc plate. Right, so that we've got the frequency for zinc is 7.4 by 10 to the 14, and we want lambda, which is equal to C over frequency, 3 by 10 to the 8 over the frequency, 7.4 by 10 to the 14. That equals 4.05 10 to the minus 7, which equals 405 by 10 to the minus 9, which equals 405 nanometers. In an effort to eject photoelectrons from the aluminium plate, we increase the intensity of the light beam, but still finds that no photoelectrons are emitted. Explain how this observation supports the particle model of light, but not the wave model of light. Alright. If light was purely a wave, so I'm going to explain this one first. Light was purely a wave. One would expect an increase in intensity would get electrons ejected. Alright, but light isn't purely a wave, is it? So, particle model supports this observation. As light exists as particles called photon, with energy of photon equals hf, and therefore increasing intensity only increases number of photons, as each electron may absorb one photon. This won't increase its energy. Well, bit of an explanation there, but I really made sure I answered this question. So light was purely a wave. One would expect an increase in intensity would get electrons ejected. But the particle model supports this observation, as light exists as particles called photons, with each energy of each photon equal to hf. Therefore, increasing the intensity doesn't affect this equation at all. So it only increases the number of photons. As each electron may only absorb one photon, this won't increase its energy. Oh no, sorry, wrong one. Open 1C and D. And in another experiment, VCE uses light of this frequency to eject photoelectrons from a sodium surface. The work function is 2.28. Calculate the maximum kinetic energy of these photoelectrons. So this is Einstein's equation for the photoelectric effect, equals HF minus W. I'm going to do the HF first. In this case equals 6.63 by 10 to the minus 34 by frequency 7.5 by 10 to the 14, which equals, where have I got it? 4.97 by 10 to the minus 19. Now that's in joules. That's in joules, this little section here, I've worked out in joules. This, the work function, is in electron volts. We've got to make them the same units. So I'm now going to turn this into electron volts by dividing by 1.6 by 10 to the minus 19, which gives me 3.11 electron volts. So now I've got everything in the same unit. So it equals that in electron volts is 3.11 electron volts, and the work function 2.28 electron volts. So the kinetic energy, maximum kinetic energy, is that minus that, which gives 0.83 electron volts. Alright, calculate the stopping voltage that will be required to just prevent the most energetic electrons, i.e. the ones with the most kinetic energy, from reaching the collector electrode. Well, this is the kinetic energy of the maximum kinetic energy of each electron, so that's the voltage needed to stop each electron. Easy.